Hi class. Okay, now we're going to go over our first example of actually solving a DE using power series. So these are kind of long processes. Not so much that, well, it does take a long time, but you have to really watch your work. So my advice is to go slow and take your time and write things out, right? So don't try to do too much in your head because you might make a mistake. So one small mistake here will turn into a it just snowballs, right? So my advice is to kind of work slowly and be methodical, okay? So I hope you guys have your pencils ready, because you're definitely going to have to take some notes here. So I'm going to try to go slow and give you guys time to write the things that are being shown to you, but obviously you can press pause. So make sure you're, kind of stopping and going as you go, rewinding as you need, okay? So power series solutions to differential equations. So I'm going to run real quickly through the step-by-step process. It's very just kind of generalized. Really, the work is it's much easier to show an example than it is to talk through an example. Okay, so what we're going to do is we are going to find the power series for y prime, y double prime, whatever derivative, highest derivative shows up in our DE, right? Whatever the order is. So I showed in the review video that these are actually really easy to find. Again, you're going to be doing these a lot, so if you're not comfortable with them yet, you will be. So really, these are the three that come up the most. Obviously, the third derivative is not that much harder than the second, okay? So you want to find your power series analogs, and then you're going to substitute those into your equation, okay? Then you are going to simplify your series with any coefficients that are present, okay? So if you have an x, y, for example, you're going to multiply all of your terms in your power series by x, meaning that the index for the power in x will increase by 1. So instead of being the sum of cn x to the n, it'll be x to the n plus 1, right? So you're going to kind of pull in any variable coefficients into your power series that you have, right? The third thing is we want to simplify these down to a single series, and we're going to do that by the example we had in the end of the last video. So we're going to make the indices match up, we're going to make the powers match up, and we're just going to combine it down into a single series. After we have a single series, we're going to have a couple of recurrence relations. We'll probably have a recurrence relation based upon the whatever terms I had to pull out, and then I will also have a recurrence relation that's based upon the series themselves, and we will use them in conjunction with each other in order to solve for my y function that I'm trying to solve for. And then I'm going to include any initial conditions or boundary conditions, and if possible, find the interval of convergence. Okay, so if I can actually find a closed form general term for my solution, then I can find my interval of convergence. If not, then I'll just won't worry about it, okay? So let's get started. So this is the general overview. So before we start, let's go over a quick definition, okay? And this really just has to do with, I'm not going to say existence, but just a definition of the types of points we can be centered about. So remember, our series are always centered about a value, okay? The easy value is when x is 0, when we're centered about x is 0. The Maclaurin series, those are great, but that's not always the case. In fact, that's most likely not the case, okay? So let's talk about a quick definition. A second order differential equation that is in standard form, meaning that it is monic, right? There's no first term here. So whatever variable I had here, coefficient, I divided the entire equation, and so I have a p of x and a q of x, okay? So if my second order DE is in standard form, then I'm going to have an ordinary point at x naught if p of x and q of x are both what we call analytic at x naught, right? Meaning that I can write p of x and q of x as a series, okay? In other words, my dE can be represented by a series at x naught with an interval of convergence that is not 0. So I'm not being convergent at a point. I have to be convergent either for all of x or for a radius, right? For an interval of convergence. Another way of saying that is that I can write p of x as a series and I can write q of x as a series, and those will exist such that the radius of convergence is not 0, okay? This sounds like a hard, difficult definition, but really what it's saying is that whatever function was on front here, if I divide that and it now becomes a numerator, whatever point I'm centered about can't make that function on the bottom 0. That's really all this is saying. It's a long-winded way of saying that this has to exist. What does it mean for this to exist? It means that my denominator can't be 0, meaning that if the point that I'm centered about makes the denominator 0, that's not going to be okay, right? So 6.2, we'll talk about how we deal with points that are not ordinary. Right now, we're only dealing with ordinary points. Again, if a point is not ordinary, then we call it a singular point, okay? A singular point. If you're in my linear algebra class, singular values kind of have the same connotation here, right? So a singular matrix is going to be a matrix that you can't invert, right? So a singular point is something that is going to be difficult for us to work with. Okay, so let's get into an example. So let's solve this dE, okay? As you can see, it's homogeneous. We won't get into any non-homogeneous examples until much later, if at all, in this section, I believe. So I have a variable coefficient and a variable coefficient. So remember, we talked about this a little bit earlier. When we have variable coefficients, we need to use series solutions. Unless we can use variation of parameters, okay? So I have, on this case, some initial conditions. I tried to choose an example that was medium to difficult so that you can see when we face problems how to deal with them. So the majority of your problems should be slightly easier than this. I guess this would be like an average to hard problem. So generally we don't have a lot of initial condition problems to work on in this class for the series. Generally we just want to find the series. So I chose to use an initial value problem so that we can see how that works, okay? So what we're gonna do, okay, and again, the program that I use to write up your things, your presentations, they don't work very well. They don't fit very well for these presentations. They do for the write-up. For the write-ups, I can force them to fit. For the presentations, not so much. So we're gonna have a couple of run-on lines. So obviously, when you write your notes, you can keep everything on one line. So I'm just preparing you now because it's not super pretty. I'm trying to keep it as nice and organized as possible, but sometimes it's unavoidable, okay? So what we're going to do is we're going to do this step by step. We're going to go very slowly, right? What I'm going to do is I'm going to take the power series for each of these things and substitute them in. But before we do that, remember, our power series are always centered about a value, okay? A value A, or it'll be given to you. If you have initial conditions, then notice that the value that you're centered about is going to be 0, right? Everything I'm doing has to do with 0. This is my initial value. That's where I'm centered at. So when I do this problem, I can center myself at 0 because that is my initial value. If I don't have an initial value, we're going to use x minus a, okay? So note that x naught equals 0 is an ordinary point. That's where I'm centered at, okay? The singular point here would be the value that makes this 0, because when I divide this across to make this in the standard form, I would have p of x be 2 minus x over x plus 1. X equals -1 would be the point that would make this undefined, and so that would be my singular point. Okay, so ordinary points and singular points are actually very easy to understand. I know our definition was very long-winded and very mathematical, but that is the definition of ordinary and singular. Conceptually, anything that would make the denominator, the first term, 0, basically, right? So it doesn't work with the other functions, the 2 minus x and this constant of 1 here. It's only for what makes the leading function 0 if possible. Okay, so now let's get into the problem. I'm going to substitute in my power series for y double prime, y prime, and y. Okay, so we substitute everything in to its appropriate place. So I have x plus 1 times y double prime, right? Minus 2 minus x times y prime plus my series for y equals 0, right? So very, very straightforward. We're just going to substitute in the things that we have. Notice that the indices are different for everything. N is 0, n is 1, n equals 2. And the indices on the powers of x are also different. Okay, so before I start trying to get the indices to match up and combine my series and all that kind of stuff, I want to simplify these coefficients, okay? Meaning that I'm going to separate this into two pieces. X times this plus just one of these. I'm going to separate this into two pieces. Minus 2 times this plus x times this. And this is going to stay as it is. Okay, so again, as you notice, I had to break this down into two lines because it would not fit on one. However, on your write-up, everything is much, much nicer and neater to look at. So after you go through this, you can, it should be easy to read that. So again, all I did was distribute this x plus 1 over this series. So x times my series plus 1 of my series, n equals 2, right? Minus 2 times this series. Negative and negative is a plus x of this one plus this series. My next step now, so again, what I'm doing is I'm trying to simplify these coefficients. So all the ones that have an x in them, I can multiply that in. So I can multiply x into here. Here I can't do anything. Here I can't do anything. Again, if you were to think about this being written out, this would be 2 times every single one of these things, right? It's a common factor of 2, negative 2, I should say here, right? Same thing here. This is a common factor of x here. All of these terms, if I were to write them out, would have an extra power of x. So what's going to happen is this x, since it's a common term, is going to bump this up by 1. So this will be NCN x to the n. This will be n times n minus 1 times cn times x to the n minus 1 value, right? So it's not changing the indices, it's going to change the power though. This is bumping up my power of x because it's a common term, so it would just shift everything up by 1. Okay, so again, everything is written the same. Gave me a little more room because I didn't have to have these coefficients here, right? So it all fits still on 2 lines, but a little bit nicer. So this goes from n minus 2 to n minus 1. This stays exactly the same as that. This and that are the same. This one bumps this one up by 1, and this one stays the same. Now, if you notice, these two now have the same x to the n, but they start at different values. Okay, so that's like that second example that I had from the review video. Okay. We have a same sort of situation here. I have different indices, starting indices, but the powers of x here match up also. Okay, so I'm getting things to kind of coalesce a little bit here. So I am going to come to my next term. So before we come to the next screen, let's just kind of think about what's going on here, right? So I'm getting some things to match up, but my indices are not the same. So now that I don't have any crazy coefficients, I do have some like negative 2s and things like that, but that's fine. What I want to do is I want to start to combine these series. So I want to check to see where everything starts at. Okay, if I plug in 2 here, this is going to give me an x. If I plug in 2 here, I'm going to get a constant. This is going to give me a constant. this is going to give me an x, and this is going to give me a constant. Okay, so this one and this one is an x. So if I take this, this, and this, because they all start at x to the 0 power, if I pull out one from here, one from here, one from here, then everything will start at x to the first power. Okay, so again, I'm finding whichever one has the highest. So for instance, if this started at x squared, I'd try to get all of these so that their indices start at x squared also. Okay, but right now, the first one and the fourth one, they start at x to the first power, or just x. All the others are x to the 0 power, right, or just a constant. So this one, so the second, the third, and the fifth, I'm going to pull one term out, so everything then starts at x, right, x to the first power. So again, I hope you wrote this down, because on the next screen, all of this is going to go away. I can fit on the next screen, but we will talk about that, right? The second, the third, and the fifth series need to pull out one term each, so all of the series start at the same power of x, okay? And that power of x is x. So when I evaluate here, I'm going to have 2 times 1, which is 2, times C2, constant, so 2C2 from here. From here, I'm going to get negative 2C1. Remember, this is just a constant, so negative 2C1. And from here, I'm just going to have C naught. So those are the three terms that are going to come out. Negative 2C2, negative 2C1, plus C naught. And now all of this will be n equals 3, n equals 2, n equals 1, because I pulled out one term from each of those, right? So those constants I pulled out, this stays the same. I didn't do anything to it. This one was n equals 2. It's now up 1 because I pulled out this term. This is now n equals 2. It was 1 because I pulled out this one. And I think it's this one is now starts at 1 because I pulled out the C naught constant. Okay. So now all of these start at x, right? I pulled out all the constants. So now the next term here is some constant times x. The next term here is some constant times x. The next term here is some constant times x, some constant times x, some constant times x, right? So now everything starts at the same place. These don't go away. This is going to stay with me through the rest of the problem. So don't just get rid of your constant terms you pulled out. This is all equal to what we started with so far. So now that everything starts at the same power of x, I need to get the starting indices to match up. So again, what we do is we make a k substitution. Each of these get their own k subs. The k subs do not come from here. The k subs come from the power on x, because all of these are going to end up being x to the k, x to the k, x to the k, x to the k, x to the k. So this is one k sub. This is the next k sub, the next k sub, the next k sub. Okay, each of these have their own k substitutions. All right, so in order, this one is n minus 1. This one is n minus 2. This one is n minus 1. K is n. K is n. And then the next step is we take each of these independently and we solve for n, not for k, because here I see n everywhere. So I have to substitute something for n so that it turns into something in k. So I solve this for k, solve this for n, solve this for n, solve this for n. These are already n's. Okay, so add 1 to both sides, add 2 to both sides, add 1 to both sides. So here, everywhere I see n, I will put k plus 1. So this will be a k plus 1 equals 2. So when I move, let's just go to the next screen. Let's just do that. So here I put in k plus 1 equals 2. And so I subtract 1 from both sides. It is now k equals 1. This n turns into a k plus 1. Okay, because that's my substitution. And this n minus 1 is now k plus 1 minus 1, or just k. Right? So this k comes from this second term. This second term comes from this first term. This is no longer cn. My substitution is k plus 1. So I have c, k plus 1. This will be x. I'm sorry, just k. All right, so that's the first one. Next one, the same thing. When I plug in n is k plus 2 here, and then I minus 2 on both sides, I get a 1. I put k plus 2 here, k plus 2 here, so this n is k plus 2. This one is k plus 2 minus 1. Right, this is k plus 2, and now this is x to the k. Same thing here for the second one, it's k plus 1 everywhere. So k plus 1 equals 2. I minus 1 gives me k1. This n is now k plus 1. This n is k plus 1. And this is k plus 1 minus 1, which is k. And these last two, everywhere I see n, I just put k. It's a straight direct transformation here. So this is k equals 1, k, ck, x to the k. Same thing here, ck, x to the k, k equals 1. So here, these ones already match up. So what I did was I combined them right away. Okay, I was just trying to get a head start. So these two I added. So if you notice, instead of n's, it's k's. But if I were to combine these, I would have a common term of cn x to the n, cn x to the n. There's n of them here. There's 1 of them here. So there's n plus 1. But the substitution was k, so it's going to be k plus 1, not c to the n, but c to the k, not xn, but x to the k, right? So I combined these two together because they were already on the same level. They're already in sync. They're already ready to go. So just to clear up space again, because I said this stuff does not, obviously is very long, right? So I just wanted to free up some space, so I put these two series together, okay? So now the next thing I want to do is I want to start to try to combine things together, because now my indices match, okay? My indices match. My powers match, okay? My powers match. I don't have any more ck terms here. This is ck plus 1, ck plus 2, ck plus 1. But what I can do is, if you notice, these two are identical. They start at k equals 1, they all do. This is x to the k, they all are, okay? But the coefficient terms are c to the k plus 1. This is not c to the k plus 1, this is not c to the k plus 1, right? So just like these had identical terms for me to combine, these two have identical terms for me to combine, right? So they both have ck plus 1 to the xk, but they also both have k plus 1. So there's k plus 1 c to the k plus 1 x to the k's here, and there are negative 2 k plus 1 c to the k plus 1 x to the k's here. All right, there's k of them here, there's negative 2 of them here. It's a common factor. These three terms here are common in both. So if I were to say this thing minus this thing, I can pull out a common factor of k plus 1, ck plus 1, x to the k. So the k minus 2 gets its own set of parentheses. Okay. So what does that look like? I'm going to have this term still. Okay. Again, it doesn't fit nicely, so this is on top, and then I'm writing the series below. So the ck plus 1 xk's, they get their own thing, right? The common factor, x minus 2, when you factor it, times their common factor that I pulled out, plus the ck plus 2 part, so k plus 1, k plus 2, times ck plus 2, right? So this is gone now, and then this is the only one that's left, k plus 1, c to the k, and all of these have an x to the k term. So square brackets just to help you identify that, you know, this is one set of parentheses. So, and then there's a bunch of smaller parentheses going on inside, obviously, right? So I have this term. So these constants I pulled out plus this series is going to equal 0, right? So now I've combined them all into one series times one variable term. So all of these are just the coefficient parts. So what we're going to do then is, since this equals 0, obviously these have to add up to 0, and this series has to add up to 0. So remember, k is your index now. It counts out. It starts from 1 and it just continues. So again, it starts at 1. Maybe we had another problem where this k ended up being 3. Our k would then start at 3. So it's important for you to remember this right now, because I'm going to reference it again in a couple of minutes. Okay, so my starting index for k right now is 1. So this has to be 0, and this general term has to be 0 for basically all k, right? So I get that the constants I pulled out are 0, and my recurrence relation has to be 0 as long as k is a positive integer. So remember, z is a set of integers. Plus means I'm looking at the positive integers, 1, 2, 3, 4, etc., etc., etc. Okay. All right. So I have that this is 0, and then I have that this is going to be 0. So what I want you to notice here is, yeah, I know it looks complicated. We'll talk about how to deal with this right now. So I kind of always think about these things as like sort of like a 3-step process. The first step is making the substitution into my series and simplifying them. The second step process is combining them all to sort of one series. And then this is the third step of the process, which is finding out all of the coefficients I need from my series, right? So we're kind of on the last phase here. I know it's a lot of work. It can be kind of confusing, right? So definitely reference your book a little bit and maybe watch this video one more time. Definitely do some examples. Doing only one example is not going to be very healthy. My suggestion is maybe after you finish watching this video, I do have a classwork problem for you, but maybe you go back to the beginning, you write this problem out at the start, right? Just the problem with the initial conditions, and then do it on your own without looking at your notes and see how close you can get to the correct answer, right? So if you haven't been doing that, I think that's a good way for you guys to approach these videos, is to watch me go through the example, then put your notes away, and then do the example again yourself and see if you can replicate the same solution, right? So what I want you to notice is that for this recurrence relation, there's a common factor of k plus 1 in all of the terms, right? This thing plus this thing plus this thing is 0, and all of them have a k plus 1. It equals 0. So if I divide everything by k plus 1, it disappears. Okay, so I don't need that extra common term when I'm equal to 0 because it's unnecessary, right? So that's nice because it simplifies it a little bit. So I have this. Okay, so whenever we have this situation for both of these, right, we have multiple constants. Even if it was only 2, right? Even if it was only, if this 2c2 was gone and I had only these two, you always solve for the largest sub-indexed coefficient term, okay? So here, my largest in this case is c2, so I'm going to solve for c2 for the first one. Here, my largest is c to the k plus 2. So for this, I'm going to solve for the c to the k plus 2. That's how I build my recurrence relations. Okay, so this isn't necessarily a recurrence relation yet. We're going to build them, but we use the pieces from our combined simplified series form. Okay, so if I solve for c2, I'm going to subtract c naught, add to c1, and then divide everything by 1/2. And that's going to simplify to just the c1 minus c naught. Okay. For this one, the same thing. I'm trying to solve for c to the k plus 2. So I'm going to subtract ck. I'm going to subtract k minus 2 ck plus 1, and then divide both of those by k plus 2. Okay. So same thing. Now, when I did that, I pulled out the negative because I had to subtract this and I had to subtract this. So we all know it's easier to keep things positive. So I just distribute the negative out, but I don't think that's super helpful because what's going to happen is I'm going to end up distributing this in anyways. Now you might be like, well, this is easier because I can just add a bunch of stuff and then throw it over the denominator. That's true. But but this might be easier because now you're looking at one term compared to another term when you start to do this. Again, you might be like, I don't know what you're talking about, Professor, and that's because we haven't done the example yet. But I do find personally that it's easier to keep things like this than like this as we work our recurrence relation. So maybe you try both. As long as you don't get confused, that's what really matters. Okay. So let's start talking about how to find our terms. So again, this is now in that third phase where we're finding the solutions. In this example, we're actually going to have 4 phases because we have initial values to consider. Okay. All right. So these are 2 recurrence relations. We have this and we have this. This is going to help us get started, and we're going to use this. We're going to use this depending on how we use this thing. Okay. So our constants, C2, it relies on 2 other constants, meaning we have a free variable. We can allow either one of these to be whatever they want to be, and C2 basically is based off of 2 different things instead of one thing. Okay, so on the easier problems, you will have one variable based on the other. So again, I chose one that was a little bit more complex. So here this C2 is based on 2 different variables. The case for when you have only one of your variables based off of only 1 and not 2 is identical. It works the same way. Okay. That's why I chose the more complicated portion. So what we're going to do is we're going to alternate our 2 free variables, but letting them take on different values each time. Okay, so for the first time, I'm going to let the smaller one be 1 and the larger one be 0. I could have said 2 if I wanted to, or 28, but that doesn't make any sense, right? So we always use 0 and 1 because 0 and 1 are nice. So we say 1 goes away and let 1 be 1. So in this case, I will have C2 equals -1 half, right? Because C0 will be 1. Then what I'm going to do is I'm going to use those with this recurrence relation. Okay, I'm going to find a few values, however many I think is necessary. Okay, basically we generally do like 4 or 5 non-zero terms. It's pretty consistent with the way that we do these things. And then what I'm going to do is I'm going to alternate. I'm going to let C0 be 0, and I'm going to let C1 equal 1, and I'm going to do the same thing. So I'm going to have 2 different kind of conditions. This is going to give me one solution, which I'll call Y1. This will give me a completely another series solution, which I will call Y2. And again, even if it was like C1 equals C0, right, or negative C0, I would still get 2 different recurrence relations, which I would use to solve. Okay, so again, I took the more complex one so we can see how this works, right? So we're going to start off with the first case. C0 equals 1 and C1 is 0, right? So for the first case, I get C0 is 1, C1 is 0, which means that C2 is C1 minus 1 half C0, but C0 is 1 and this is 0, so this is going to give me just -1 half. Okay. Now you might be saying, well, that's nice. Does that mean I'm done? No, it does not mean we're done. We have to find the rest of our terms. We need to use this recurrence relation. So when I said 4 or 5, I meant 4 or 5 using this recurrence relation. This just helps us to get started. Okay. So from now on, I've used this C2 as much as I can. Okay. So now for C3, C3 is going to be based off of K. Right. Remember, we are starting at, in this case, K equals 1. That's where I start, right? So, okay. So now if I let K equal 1, this turns into my C3, right? And it should always work that way, that the next one that I need is based off of my value of K, right? So K equals 1 means that I have C3 here. So I'm plugging that into this recurrence relation, right? So I have -1 minus 2. 1 minus 2 is a -1. 1 plus 2 is 3. So I got -1 over 3 times K is 1 here. So 1 plus 1 is C2, which I just found before, right? So I'm using the previous values to find my next value. That's why it's called a recurrence relation, right? Over here, I have minus 1 over x plus 2, so I'm using 1 over 1/3, right? Because 1 plus 3 is 1/3, times c to the k. So c of 1 is 0. So I wrote this wrong. I should have wrote negative 1/3 times 0, because c1 is what's 0. I'm not getting 0 from this out. Okay, so apologies for that. Hopefully it doesn't confuse you. I don't think it should. But regardless, this is 0. So I'm basically getting a negative 1/3 or positive 1/3 times c2. And what's c2? Minus 1/2. So I get a 1/3. This is positive, right? Positive 1/3 times a negative 1/2 is a negative 1/6. Right? So that's what I have for c3. So now I'm going to go to k equals 2. K equals 2 means that I have c of 2 plus 2, or c4. And then I'm also going to plug in 2 everywhere here. So notice when I plug in 2 here, this goes to 0. So this first term will be 0. And this will be 1 over 4 c2, because I'm at 2, right? And what is c2? Minus 1/2, right? So c4, c of 2 plus 2 is c4, equals 2 minus 2 on top, which is 0. So I don't even have to worry about anything else. Minus 1 over 2 plus 2, which is 4, times c of k, which is 2. Okay, so c2. So what is c2? c2 is minus 1/2. So I have minus 1/4 times a minus 1/2, or a positive 1/8. So c0 is 1, c1 is 0, c2 is minus 1/2, c3 is minus 1/6, c4 is 1/8. So I've used k twice. Let's do it a couple more times, right? 3 is okay, 4 is good, 5 is great, right? I think I did 2 here just to kind of get it all to fit here. When I did in my notes, I did like 4 or 5 of these. So I think we're going to stop at k equals 3 here. This is good enough for what we need. So this is going to give me c5, right? Obviously I'm counting up. c0, 1, 2, 3, 4. The next one is 5. And that should make sense. If I plug in 3 here, I get c of 3 plus 2, or c5. So this is what it'll look like, right? I have k is 3, so 3 minus 2 is a 1. It's still negative on the outside. 3 plus 2 is 5. Okay, same thing here. 1 over 3 plus 2, right? And if you notice, the values on the first one, my recurrence relation, are increasing. c1, c2, this was 0 times c3, this is now c4. And the second term are also increasing. 0, c1, c2, c3. If I did one more, it would be times c5 and c3, times whatever I needed to plug in here. Okay, so there's always a pattern here. So what is c4? That's the last one I had, 1/8. c3 was the one before that. So this is negative 1/5 times 1/8, or 1/40th. And this is minus 1/5 times a minus 1/6, because that's c3. So minus 140 plus 1/30th. So multiply this by 3, this by 4. Okay, so that's our common denominator, or 1/120th. So that's the first 5 terms. 5 terms is pretty good. The first 3 terms were easy to find. The next 3 terms I found through this recurrence relation. So, 3 and 3, that's pretty decent here. Okay, you can do more. You can do as many as you need. More is always better. Okay, but obviously you can see that the numbers are getting more and more complex as you go. So around 5 or 6 are good. Okay. So my y1, okay, so again, remember, power series, right? Constant times x squared times x cubed times x to the 4th times x to the 5th. Now, if we were the power series centered about, let's say, x equals 1, we would need to make sure that we had this as 1/2 x minus 1 squared, right? But here, we are centered about x equals 0 because of our initial value. So again, these values are just those coefficients that I had. 1, there is no x term, negative 1/2 times the x squared, okay, negative 1/6 times the cube term, 1/8 for the fourth term, and 1/120th times the fifth term, and then it continues to go. Remember, this goes on forever. This is a series. It does not end. Right? So now what we're going to do, instead of saying C1 is 0 and C0 is 1 and C1 is 0, we're going to switch. We're going to let C0 be 0 and C1 be 1. So again, remember that when I'm done, all of my answers here are based off of the assumption that C0 is 0. So at the very end, I'm going to keep this variable, or this coefficient C0, times this solution that I just found. Okay, and then once I do this for C1, all of my coefficients that I find for y2 are based on C1. I'm just assuming that it's 1 for right now, although it can be any value. So at the end, I'm just going to take my answer for y2 and I'm going to multiply it times the coefficient C1. Okay, you'll see what I mean by that later. So here we're swapping which one is 0 and which one is 1. So C of 0 equals 0 gives me this. C1 is going to be 1. C of 2, remember, is C1 minus 1/2 C0. C0. So I'm going to have 1 minus 0, or just 1. Okay. For K equals 1, I will have this. So again, you can verify, because I don't have the formula for you here, right? But remember, it's K minus 2, K plus 2, 1 over K plus 2. If I'm at 1, K plus 2 means that I'm at 1 plus 2, or C3. Negative 1 minus 2, 1 plus 2, 1 plus 2, right? So this is positive 1/3 minus 1/3, or 0. Okay, so the first term goes away. So K equals 2. Again, I'm going to have 2 minus 2 up here, so this whole first term goes away. This should be 1/4 C2 on the next one, right? So what was C2? C2 was 1, so this will give me a negative 1/4. K3 is going to give me a, so this was C2, this 0 term was C3, so the next one will be a C4, right? So negative 1/4 times, and then what happens when I plug in 3 here? So 1 over 4, or sorry, 1 over 5, because it's 3 plus 2. So C4 is the first coefficient here, C3 is the next because it's increasing by 1. So this has the same denominator, right? They always have the same denominator in this case. So what was C4? C4 was negative 1/4. What was C3? C3 was 0. So I only have negative 1/5 times negative 1/40, or 120, right? So when I throw all of these together, the constant is gone. 1 times x, C2 is 1, so that's an x squared. The x cubed is gone. Negative 1/4 x to the 4th, and this is my x to the 5th term. Okay, so that's my y2. So remember, this is what my answer looks like, and y1 is all based on C0, and all of my y2, I need to fix that, sorry. All of my y2s are based off of C1. Okay, so y equals 0. Okay, y equals 0. This all goes away because all of these have x's. There's no constants. Here, all of these go away, and I'm left with 1 C0. Right? So that means that C0 equals 2. So that means I would take 2 and multiply all of that y1 function times 2. Okay, so I'm going to get 2 minus 1/2 times 2 is a negative 1. So everything in y1 doubles. For C1, I don't know what C1 is, so I leave that alone. Okay, but the C0 function is actually 2, and since all of these values were reliant on C0, I have to bump them up according to what the C0 actually is. Right? So I'm going to do the same thing with the other initial condition, which is y prime of 0 equals negative 1. Okay, but before that, obviously, I need to find the derivative. So I differentiate all of these terms that I have so far. Okay, so this 2 goes away. This turns into negative 2x. These cancel, and I have just minus x squared. This turns into just an x cubed. This is 1/12 x to the fourth, and whatever else would be there. And then I also differentiate these terms, right? So x goes to 1, a 2x. This turns to just a negative x cubed, and this turns into a 1/4 x to the fourth. Right? So now I apply the initial condition for the derivative. I'm plugging in 0, so this whole thing goes away. Okay, everything here goes away, and I'm left with c1 being -1. So then I do the same thing I did over here when I found out c0 was 2. I come and I multiply everything by -1, so everything in c1 just changes signs. And so this is my answer, right? I have my original thing when I multiply everything by 2 by c1, and for y2 I multiply everything by -1, so all the values are the same. I'm just changing their sign. And if you notice, I have some like terms. I have some x squares to combine. No x cubes, but I have some x to the fourth that I combine. And I have some similar x to the fifths. So when I combine my like terms from what I have, this is what my answer looks like. So I have the first 1, 2, 3, 4, 5, 6. First 6 terms of my series. If I could identify a pattern very easily, I would write a general form here, right, for my solution. I couldn't find one. I didn't spend a lot of time, to be honest, to try to find it. I just want to find the solution. But if it's easy to see, you can find the general form here. Maybe your general form has the power series approximation for sine in it. And so maybe your answer is really something like some series plus sine, right? Or some series plus cosine. So for instance, maybe I saw here that C1 was alternating in a way that looked just like the sine series. I would say, hey, this is just the sine series, right? So then I would say I have something plus sine. My y2 would be sine. So just be on the lookout for that. I'll try to post a link that has the common power series for like e to the x, natural log of x, cosine of x, sine of x, those things, the common power series that you would play with in Calc 2. But for right now, this is my solution. Again, if I could identify a general form for the series, then I would, and then I would find my interval of convergence for it. Okay, so just a heads up that would be a full level problem, right? It's find the interval of convergence for your solution. Most likely on an exam, I'll say, hey, I want you to find the first 6 terms of this, 6 non-zero terms of the solution to this DE. Okay, so that is your example. And I have a classwork for you. This will be due tonight at midnight. Make sure to write up all your steps. Good luck.